Muppet Labs, where the future is being made.
Why do we need replenishable power? In this modern age, we are faced with a crisis of energy supply. Oil is running out, and this source of energy is the product of animals that died eons ago, slowly being rendered into this non-renewable source. Many people have objected to wind farms, either as ugly, noisy, or a risk to birds. But pylons have been around in the environment for a long time and service only the power companies' profits. Windmills were used long before oil and electricity came along, and some of the old ones still exist. Arguably, the modern slender ones are much easier on the eye and far more powerful. Gas shale is now on the agenda, which is essentially the last gasp of the oil industry. Destructive drilling of the environment is perhaps more of a problem than a myriad slender windmills. Gas shale drilling uses a lot of energy in order to release the end product, as indeed does oil. Continuous CO2 production from burning fossil fuels is destroying the Earth's atmosphere, so we need fuel that does not create toxins. Nuclear power, of course, suffers from the requirement of mining for raw materials and the creation of radioactive products that are a result of processing. Accidents that have happened at Harrisburg, Chernobyl, Fukushima and Sellafield have caused dangerous radioactive elements to be released. Recent news suggests German scientists may have had some success with fusion, which in theory mimics the power of the sun to produce energy, and does not have some of the dangerous side effects of fission, although holding a small star in place is not easy nor particularly safe. We have potentially two types of nuclear system that can supply energy: fusion and fission. Fission creates radioactive elements that then have to be reprocessed. This also creates a security hazard, as nations can use this to create nuclear bombs. Fusion exploits the power of the sun to supply nuclear energy and works in the same way as our star. In principle, this is a better system, but no one has managed to render it stable and usable except for Tony Stark. The national power grid also keeps people beholden to the power companies, and there is no way one can put a nuclear power station in one's own back garden. So in order to get away from centralized control, and in order to supply energy that will always be available, we need renewable sources now, not when someone comes along with the genius of Tony Stark. We cannot wait. According to physicist Brian Cox, even if we had fusion power available, this still would not supply the energy needs for the future. Local personal energy supplies are off-grid. Both remove centralized control and paying bills, and are far more efficient because sending central power around the grid loses energy through kilometers of cable resistance, which is why it is thousands of volts when it leaves the source and hundreds of volts when it reaches homes, and has to be reduced again to power most electronic equipment to 12 volts or so, losing power to heat in the process. Renewable power never runs out, doesn't lose power to a grid, and is therefore more efficient. It stops ongoing bills from having to be paid, though it may require initial investment. Renewable power is fairer for the individual and enables them to control their own power use rather than being dictated to by large corporations. Indeed, one can end up selling excess power to the national grid and profiting from one's own production. There are some difficulties involved in going off-grid, including the initial financial investment and planning permission. Notably, some of the processes involved in creation of such things as solar panels and wind turbines involve metal and plastic processing, which themselves rely on oil and electricity for production. It may be that we have to return to building from wood as ancient water wheels were, which is replenishable. One of the benefits of renewable power is it needn't be part of the national grid. It could be solar panels on a single house in the middle of nowhere, a windmill on a farm, or it could be actually attached to the device that it needs to power, as in the case of solar cells on calculators, or indeed a solar-powered car. Muppet Labs at MTVCA has undertaken some experiments with respect to renewable energy in the fields of wind, hydro, solar and chemical. Obviously we're not going to mess about with nuclear, although apparently making your own fusion reactor is child's play, not that we are going to attempt it. We will now show some of the experiments that the MTVCA has carried out. The advent of modern wind turbines has caused some controversy, not only because of their intrusion into the landscape, but because of the suggestion of them killing birds and bats. Jet aircraft kill birds, but do not get the same sort of criticism because people perceive the need for aircraft. Engineers are working on ways to stop modern turbines from causing problems for animals. The same objections have not been levelled at the old windmills, which are still seen as aesthetic, and yet modern turbines arguably look better than pylons which are spread across the country. Smaller 12-volt and 24-volt turbines don't need to impinge so much on the environment, and are not so much a danger to birds and bats. They also produce power without the losses incurred from central production, because the voltage is already at the level needed at the site, and in most cases electrical equipment can use the voltage without recourse to a transformer, or an inverter can be used to supply the required 240 volts. A criticism of turbines is the capacity to only produce when there is wind, but that is the whole point, to capture the power of the wind when it is there and store it in a battery for later use.
Wind energy has been used for thousands of years for milling grain, pumping water and other mechanical power applications. Attempts to generate electricity from wind power have been made since the end of the 19th century. Small wind turbines for charging batteries have been manufactured since the 1930s, but it is only since the 1980s that the technology has become sufficiently advanced for large-scale power generation. Wind power is now one of the most cost-effective methods of electricity generation and one of the fastest growing. A total of 31,000 megawatts of wind generating capacity has been installed by the end of 2002, about 4 times the capacity at the end of 1997, an annual growth rate of 40%. The Earth's wind systems are due to the movement of atmospheric air masses as a result of variations in atmospheric pressure, which in turn are due to the uneven solar heating of different parts of the Earth. Wind energy was one of the first sources of energy to be exploited by early civilizations. Windmills are believed to have existed for over 4,000 years. Many early windmills were of the vertical axis type and had a variety of designs. The more familiar horizontal axis windmills appeared in Europe in the 12th century. These traditional machines consisted of radial arms supporting sails that rotated about a horizontal axis. Before the Industrial Revolution, it is estimated that there were 10,000 of these windmills in Europe. Modern wind turbines can be of the horizontal or vertical axis type, and a variety of designs have been proposed over the years.
One of the first projects we undertook was to develop a small-scale portable wind turbine suitable for charging AA-size batteries. This device provides an alternative energy source using free energy from the wind. The aim was to construct this using recycled materials as far as possible. The range of devices which use power in this form is large and growing from mobile phones and digital cameras to remote controls and battery-powered clocks. We discard millions of batteries every year, and even when we use rechargeable cells, charging them from AC mains is a very inefficient way of using energy, as much of it is lost in the transformer. Any renewable energy device requires a certain amount of energy to manufacture it, so a key measure of such devices is the return on energy invested. The device has to generate the same amount of usable energy as was used to manufacture it before it starts paying for itself. By making use of recycled materials, less energy has to be invested in constructing the device, and this also gives a new lease of life to discarded materials which would otherwise end up in landfill. The dynamo is the bottle dynamo type used on bicycles, which can be obtained for a few pounds. The housing for the dynamo is made from packaging containers, standard size food tins, pop bottles, or offcuts of drainage pipe. The blades are made from a length of plastic drainage pipe about 7 cm in diameter and 30 cm in length. The pipe is cut into 3 sections using diagonal cuts, so that the section gets narrower and is offset at the narrow end. This creates a twist in the section which forms the aerofoil. The blades are coupled to the axle by attaching them to a short piece of plastic tube. We want the turbine to be able to pivot horizontally so it can turn into the wind. To achieve this, the housing was mounted on a pivot made from a caster removed from a piece of old furniture. The wheel was removed and the can is fixed to the caster using a band of metal. A tail fin is made from a piece of sheet plastic and attached to the back of the housing to help the turbine turn into the wind. A small hole drilled in the side of the can where the caster attaches allows the wires attached to the stator coils to exit the housing. The caster is attached to a wooden support pole by means of a hole drilled vertically in the top of the pole. A cross piece provides a base for the support. Guys are attached to the pole near the base using picture hooks. These should be low enough so that there is enough clearance for the rotating blades when the ropes are fully extended. When the turbine is deployed, the ropes can be secured to the ground to provide stability. The output from the dynamo is alternating current, so a rectifier circuit is required to convert this to direct current suitable for charging a battery. The turbine bought with the You Choose grant has been deployed and is under test, although we don't have a decent regulator for its three-phase supply yet. Over Christmas 2015, the UK has suffered flooding in many areas. With such large quantities of water dropping, it makes sense to collect it and use it as a source of hydropower. Over the past few months, what has been evident in the UK is a large amount of wind and truckloads of water. So much water that it has flooded areas of the UK. Some have put this down to housing being built on floodplains, which is no doubt true, and that the government has been lax in dredging rivers, which is also true. What may also be the case is that the floods are the consequence of global warming, which has caused sea levels to rise, raising the level at inlets and at the coast. It is relatively safe to say then that the UK has sources of wind and water in abundance, and along with the turbines collecting wind, that we can have water wheels gathering power from water sources.
Moving water was one of the earliest energy sources to be harnessed. Irrigation systems existed at least 5,000 years ago, and it seems likely that the earliest water-powered device was the noria, used to raise water for this purpose. This device appeared in the Middle East and Far East earlier than 600 BC. The earliest water mills were probably vertical access corn mills known as Norse or Greek mills. These appeared during the 1st century BC in the Middle East and a few centuries later in Scandinavia. In the following centuries, increasingly sophisticated water mills were developed throughout the Roman Empire, the Middle East and Northern Europe. The Domesday Book recorded over 5,000 water mills, suggesting that every sizable settlement had its own mill. During the following centuries, water became the main source of mechanical power for mining, ironworking, papermaking, and the wool and cotton industries. By the end of the 17th century, England had 20,000 working mills. Up until about 1800, investigations were made into different designs. The overshot wheel is driven by water falling from above, on blades with closed sides. It requires a head of water at least as high as the wheel diameter. The undershot wheel is driven by the pressure of water against its lower blades, which dip into a flowing stream. It can be run from almost any stream, but becomes inefficient if the water backs up due to flooding. The breastshot wheel has the water channeled so that it strikes the blades at about the level of the wheel axle. It is a compromise between the two and overcomes the flooding problem without requiring such a high head as the overshot wheel. A number of developments took place in the 19th century, which led to the development of hydroelectric power. In 1832, a French engineer named Benoit Furneron developed the first successful water turbine. This was a vertical axis machine in which the turbine runs completely submerged. Guide vanes inside the turbine direct the water flow onto the moving blades, ensuring the smooth flow of water, resulting in an efficiency of as much as 80%. By 1881, the world's first public hydroelectricity supply opened in Godalming in Surrey. The capacity of individual power stations grew to over a megawatt in less than a decade, and hydroelectric generation continues to expand today.
We have built a Pelton wheel from an old bicycle wheel and got this turning from a flow of water, supplied from a tank at the top of the hill, which collects rainwater runoff from the garage. The idea is to get this to turn a dynamo. Calculations suggest it should generate about 5 watts.
doing it now. Got it? Yeah.
The problem with the water wheel is that the tank of water powering it is soon exhausted. In order to improve the situation, the arrangement can be enhanced using a pump storage system. Water from the garage roof is collected into the IBC tank to act as a source of water for the Pelton wheel. Water flowing downhill from the tank initially is used to drive the dynamo in the Pelton. A wind turbine is used to pump water uphill to the tank to recreate the potential energy and resupply the Pelton with its driving force of water. This uses wind to recover water lost from the tank in order to be released again to power the dynamo in the Pelton wheel to produce electricity. This is then stored in batteries to be tapped at will. There are several ways to use the sun's energy, but the MTVCA invested in 2 solar panels using the You Choose grant, which now adorn the headquarters.
The discovery of the photovoltaic effect is credited to French physicist Edmond Becquerel, who described an experiment in 1839 in which the voltage of a battery increased when light was shone on the silver plates of the cell. In 1877, 2 Cambridge scientists, W. G. Adams and R. E. Day, described variations in the electrical properties of selenium when exposed to light. In 1883, Charles Edgar Fritz constructed a selenium solar cell similar to the silicon solar cells used today. These cells were very inefficient, converting less than 1% of the light into electricity, but they did find a use in photographic exposure meters. The breakthrough which led to modern solar cells came in the 1950s. A team of scientists at Bell Telephone Labs were researching the effects of light on semiconductors. In 1953, the team produced devices made from silicon which were much more efficient than earlier devices in producing electricity from light. Over the past few decades, progress has been made in improving the efficiency and reducing the cost of PV cells to the point where they can be used commercially. A growing number of domestic, commercial and industrial buildings now have PV arrays providing a substantial portion of their energy needs. As early as 1958, solar cells were used to power the radio transmitter of the American Vanguard satellite, and have become the standard power source for modern spacecraft such as the International Space Station. As costs have fallen, the amount of installed solar generation has increased, and this trend seems likely to continue in the future.
One way to make use of solar power is with photovoltaic cells. These rely on the effect of semiconductor materials to convert the energy in sunlight into electricity. Solar panels fitted on the wall of the MTVCA headquarters are providing electricity to charge batteries in the cellar workshop. A variation on this idea is the photogalvanic cell, which was developed in the 1950s. In these devices, the energy of sunlight is used to reverse the effect of chemical reactions in the battery, causing it to recharge. They have the advantage of storing energy, but so far they have not been developed to the point where they can be used commercially. With the U-Choose grant given to the MTVCA, we were able to purchase two 80-watt solar panels which were erected on the front of the house. These feed down into the cellar and into a control box which is being fabricated from an old amplifier. Currently, one solar panel is charging the main battery which powers the LED lamps in the cellar. The case is merely a housing for experimental circuits, but at the moment is able to charge small batteries which light the hide and sheds in the garden. Shortly the lighting in the stairwell to the basement is to be replaced by efficient LED lights. There are also small solar arrays, one of which was used at the U-Choose presentation in order to secure the grant.
If the sun's rays are concentrated using mirrors, high enough temperatures can be generated to boil water to drive steam engines. These can be used to provide mechanical work for electricity generation. These systems have a long history, and if cheap oil and gas had not appeared in the 1920s, solar engines might have developed to be commonplace in sunny countries. The most common method of concentrating solar energy is to use a parabolic mirror. All rays of light that enter parallel to the axis of a mirror formed in this particular shape will be reflected to one point, the focus. If the rays are off-axis, they will not pass through the focus, so it is necessary for the mirror to track the sun. These mirrors can be made in either line focus or point focus. In the line focus or trough collector, the mirror faces south and only has to track the sun's elevation. In the point focus form, the mirror must track the sun in elevation, up and down, and in azimuth, side to side. The process of converting this power into mechanical work started in the 19th century. In the 1890s, France lacked a supply of cheap coal. Math professor Augustin Mouchot had the answer: solar-powered steam engines. Mouchot produced engines ranging from a solar printing press to solar wine stills, solar cookers, and even solar engines driving refrigerators. The system had a parabolic reflector with a boiler at the focus. However, the engines were not very efficient, and by the 1890s could not compete with supplies of coal appearing as the result of new investment in mines and railways. At the beginning of the 20th century, an American entrepreneur, Frank Schumann, built a system of large trough collectors in Egypt. This used 5 trough collectors 80 meters long and 4 meters wide. At the time, coal was expensive in Egypt because it had to be imported, so the system would have paid for itself in just 4 years. A more ambitious scheme involving 20,000 square miles of collector in the Sahara was planned. This would have produced 270 million horsepower, equivalent to all the fuel mined in 1909. Unfortunately, the First World War and the advent of cheap oil put an end to interest in this scheme. It was not until the 1980s that the first serious large experimental electricity generation schemes were built to make use of high temperatures. Many of these were of the central receiver or power tower type, such as the 10 megawatt system at Barstow, California. The system uses an array of tracking mirrors which concentrate the sun's energy onto a boiler at the top of the central tower. A power station at Kramer Junction in the Mojave Desert generates electricity commercially and produces most of the world's solar electricity. Between 1984 and 1990, Luz International brought online 9 systems of between 13 and 80 megawatts. These are trough collectors along the lines of Schumann's original design from 1913. Instead of conveying the steam from the collector to a separate engine, some systems have the engine itself mounted at the focus of a parabolic collector. This can be a steam engine or a Stirling engine.
The Stirling engine was invented by Robert Stirling originally to provide a safer alternative to steam engines, then being used to provide pumping for mining operations. The Stirling engine is an example of an external combustion engine. The engine consists of a hot and cold chamber, each of which has a piston, and the pistons are connected by a linkage mechanism which turns a flywheel. Heat is provided to the engine by an external heat source which causes the air inside the hot chamber to expand. This moves the piston, causing the flywheel to turn. The hot air is drawn into the cold chamber where it cools and contracts, drawing in the second piston. This turns the wheel further, forcing the cooled air back into the hot chamber to start another cycle. In more recent years, this principle has been adapted so that the heat is provided by a solar concentrator, and the engine turns a dynamo providing electrical power. Such systems have been exploited commercially, for example by Sun Power in the US, to provide renewable energy. These devices use a solar concentrator to focus the heat of the sun. We have made a solar concentrator from an old satellite dish covered in mirror tiles, which has proved quite effective. A variation of the Stirling engine is the liquid piston engine or fluidine. In these devices, the pistons are formed from columns of water. They can be driven by the heat of the sun and have been used to pump water. Our own attempt at a fluidine is still a work in progress. Another way to exploit the heat of the sun is to have it heat water up in radiators that are painted black in order to absorb its energy. In doing this, we've managed to attain water temperatures of around 50 degrees. One of the problems facing renewable energy is that the supply is intermittent. The sun does not always shine and the wind does not always blow at the time we want to use energy. For this reason, we need a way of storing energy in a form which we can use on demand in the form of fuel. One proposed solution to this problem is hydrogen. Hydrogen is a gas at room temperature and can be burned as a fuel in the same way as natural gas, but no carbon dioxide is produced when burning hydrogen, so it does not contribute to the greenhouse effect. The other advantage of using hydrogen is that it can be generated easily from the electricity produced by renewable resources, using a process called electrolysis. Electrolysis uses ordinary water, which consists of the chemical elements hydrogen and oxygen in chemical combination, and has the formula H2O. The electrolysis process uses electrical energy to split the water molecule into its component parts, releasing the gases hydrogen and oxygen, which can be stored for later use as a fuel. When these gases are brought together again, they combine in a combustion reaction, releasing the stored energy as heat. The only byproduct of this is water vapour, which can be safely released into the atmosphere. The heat energy can be used directly to provide heating or used for motive power in an engine or gas turbine. The hydrogen and oxygen can also be consumed in a device called a hydrogen fuel cell, which produces electrical energy directly from the chemical energy stored in that fuel. The standard laboratory equipment for electrolysis is called a Hoffman apparatus, but you can get the same results using homemade equipment based on simple materials such as a home brew kit or even pop bottles. As renewable energy sources tend to be intermittent, we need a way of storing the energy so that it can be made available on demand. One way to do this is to store the energy in the form of chemical energy in batteries. In this section we will have a look at how the different kinds of batteries do their job. Electric current consists of the flow of charged particles called electrons through a conductor. A battery converts chemical energy into electrical energy by means of a pair of chemical reactions. For example, one of the earliest known galvanic cells has electrodes made of the metals zinc and copper. The copper electrode is immersed in a solution of copper sulfate and the zinc electrode in a solution of zinc sulfate. The different metals have a different electrical potential when immersed in solution, so when the circuit is closed, electrons flow from the zinc electrode to the copper electrode, providing an electric current. As the zinc loses electrons, it undergoes a chemical reaction forming zinc sulfate. At the other electrode, copper dissolved in the copper sulfate solution accepts the electrons and the copper is deposited on the copper electrode. The two chemical reactions are kept separate by a salt bridge. The chemical reactions provide the energy to drive the electric current. Eventually all the zinc is used up and the cell is spent. In order to store electrical energy, we need a cell in which the chemical reactions can be reversed by applying an electric current. This provides us with a rechargeable cell. The most common example is the lead-acid battery found in motor vehicles. The lead-acid battery was invented in 1859 by French physicist Gaston Planté and is the oldest type of rechargeable battery. In this case, one electrode is lead and the other is lead oxide. Both electrodes are immersed in a solution of sulfuric acid. The lead electrode reacts with the acid to form lead sulfate, an oxidation reaction which provides electrons. The lead oxide reacts with the acid also to form lead sulfate, a reduction reaction which accepts electrons. When the circuit is closed, the electrons are transferred, providing an electric current. Crucially, this reaction can be reversed by applying an electric current in the reverse direction. Energy supplied by the electric current reverses the chemical reactions, converting lead sulfate to lead at one electrode and lead sulfate to lead oxide at the other. This has the effect of storing electrical energy for later use. An alternative to the rechargeable cell is the fuel cell. In this case, the materials required to drive the chemical reaction are continuously supplied to the cell, which will continue to operate for as long as we have a supply of fuel. A hydrogen fuel cell is an example of this. Hydrogen is supplied to one electrode and oxygen to the other. A separator between the two electrodes allows ions to pass between them to drive the chemical reaction, but prevents the flow of electrons, forcing them to travel around an electric circuit, providing the electric current. The earliest hydrogen fuel cell used an alkaline solution as the separator. These cells provided the electrical power for the Apollo space flights. Modern fuel cells use a special polymer called a proton exchange membrane. It is permeable to hydrogen ions. A hydrogen fuel cell can use the hydrogen generated by electrolysis to provide electric power. So generating hydrogen gives us a way to store electrical energy from renewable resources. Fuel cells tend to be more energy efficient in doing this than it would be to burn the hydrogen gas in a turbine. A recent Metro article provided the following stats. Wind is Britain's largest source of renewable energy. There are 595 operational wind energy projects in Britain. There are 5,425 operational wind turbines. 4,350 are onshore and 1,075 are offshore. The wind projects produce enough energy to power 6.1 million homes. Wind power could be harnessed to meet up to 20% of Britain's electricity demands. The amount of electricity produced by wind increased 38% from 2012 to 2013. Britain's first commercial wind farm was built in Delaval, Cornwall in 1991. Wind accounted for 7.7% of Britain's sources of electricity generation in 2013, up from 5.5% in 2012. However, this accounts for less than 2% of total energy demand. The government wants renewable sources to provide 15% of Britain's energy by 2020. Siemens and associated British ports are investing £310 million in British wind turbine factories, creating 1,000 jobs. In February 2014, wind energy generated 11% of Britain's electricity. On February 23rd, wind supplied 17% of electricity demand. 67% of Britons would prefer to have a wind turbine near their home than a shale gas well. These stats were part of an article that made the following points. The Tories are to cap onshore wind farm output. The Royal Academy of Engineering suggested this might lead to less UK investment and higher energy bills. The Tories believe there are enough people who see turbines as a blight on the landscape and want offshore turbines to please the NIMBYs. An economist at Imperial College pointed to the differential aid available to on- and offshore turbines and suggested the move to offshore turbines would need the gap in aid to be recovered through higher bills. In the US, turbines are breaking energy-producing records, largely because they are cheaper than coal and gas. The current move to fracking for shale gas is a short-term fix that will not outlast turbines and solar production. Two studies have produced opposing results about house prices, one suggesting the wind farms depreciate the value, and one saying they do not. The working group suggested it was bizarre to curb turbines and that it was probably a mistake to think fracking would decrease prices. They stated that most of our energy last winter was from coal-powered stations from the 60s and 70s. The infrastructure is out of date and will be pensioned off without a plan for the future. The article was followed by a volley of letters. John Davis asks what Mr. Cameron is going to do when oil runs out, and he continues to try and please the NIMBYs. He suggests we all have a turbine of our own, which also reduces atmospheric pollution. He says we should take a long-term view and not be as blinkered as politicians. Steve Dowson denounces the use of funds to make munitions rather than spend on renewable energy. Jim from London finds he has a decision to make: either accept onshore turbines, which he thinks are ugly, or face higher bills. Mr. Wilson of Staffordshire points out that there isn't any power from wind turbines when the wind is not blowing. He also suggests that we should embrace all forms of power until scientists have cracked the elusive option of nuclear fusion. Considering that the older windmills are now viewed as aesthetic enhancements to the landscape, it seems folly not to accept that our modern, more efficient ones will not be seen the same way in the future. There was also the following snippet in the same paper. World needs to shut polluting plants by 2100. Extensive cuts to greenhouse gas emissions are needed to avoid dangerous climate change, a major UN report has warned. Countries must all but phase out fossil fuel power plants by 2100 unless they have carbon capture systems, said the Intergovernmental Panel on Climate Change. Deforestation will also have to be curbed to keep global warming below the critical 2 degrees C rise, the panel said.
World consumption of all forms of primary energy increased more than tenfold during the 20th century. In 2002, this reached an estimated 451 exajoules. Fossil fuels provided 3/4 of the total. At that time, world population was 6.2 billion, so the annual average consumption was 74 gigajoules, equivalent to nearly 6 litres of oil per day for every man, woman and child. These figures conceal major differences. The average North American consumes nearly 5 times the world average, about 350 gigajoules per year. People in Europe and the former Soviet Union use about half this amount, and those in the rest of the world 1/5. How long will the world's fossil fuel reserves last? At current consumption rates, proven world coal reserves should last for about 200 years, oil for approximately 40 years, and natural gas around 60 years. However, world production of liquid fuels seems likely to reach a peak between 2005 and 2015. Peak production of natural gas is likely around 2030, and from then on will be in decline. The current use of fossil fuels has many adverse consequences, such as air pollution, acid rain, and depletion of natural resources, but we can highlight one major cause for concern: global climate change caused by the emission of greenhouse gases from fossil fuel combustion. The surface temperature of the Earth establishes itself at an equilibrium position where the incoming energy from the Sun balances the outgoing infrared energy re-radiated back from the surface into space. If the Earth had no atmosphere, its average surface temperature would be minus 18 degrees Celsius. But its atmosphere includes greenhouse gases, principally water vapour, carbon dioxide and methane. These act like the panes of glass in a greenhouse, allowing solar radiation to enter but inhibiting the outflow of infrared radiation. The natural greenhouse effect they cause is essential in maintaining the Earth's surface temperature at a level suitable for sustaining life, around 15 degrees. Since the Industrial Revolution, however, human activities have been adding extra greenhouse gases to the atmosphere. The principal contributor to these increased emissions is carbon dioxide from the combustion of fossil fuels. Scientists estimate that these human-induced emissions caused a rise of the Earth's global mean temperature of 0.6 degrees during the 20th century. If emissions are not curbed, the surface temperature is predicted to rise by 1.4 to 5.8 degrees by the end of the 21st century. Such rises will probably cause an increased frequency of climatic extremes, such as floods or droughts, and serious disruption to agriculture and natural ecosystems. Mean sea levels are likely to rise by around 0.5 metres by the end of the century, which could inundate some low-lying areas. Beyond 2100, much greater sea level rises could occur if major Antarctic ice sheets were to melt. The threat of global climate change caused by carbon dioxide emissions from fossil fuels is one of the main reasons why there is a growing consensus on the need to reduce such emissions. Reductions in the range of 60 to 80% may be needed by the end of the 21st century, and ultimately a switch to low or zero carbon energy sources such as renewables. The renewable energy sources, derived principally from the enormous power of the sun's radiation, are at once the most ancient and most modern forms of energy used by humanity. Solar power, both in the form of direct solar radiation and indirect forms such as water or wind power, was the energy source on which early human societies were based. Ancient civilizations harnessed the movements of water and wind caused by solar heating of the oceans and atmosphere to grind corn, irrigate crops, and propel ships. Technologies for harnessing the power of the sun, water, and wind continued to improve up to the early years of the Industrial Revolution, but by then the advantages of coal, the first and most plentiful of the fossil fuels, had become apparent. These highly concentrated energy sources soon replaced wind and water power in the homes, industries and transport systems of industrial nations. Today the fossil fuel trio of coal, oil and natural gas provides 3/4 of the world's energy. However, concerns about the adverse environmental and social consequences of fossil fuel use, such as air pollution and global warming, and the finite nature of supplies, have been voiced intermittently for several centuries. But it was not until the 70s, with the steep price rises of the oil crisis and the advent of the environmental movement, that humanity began to take seriously the possibility of fossil fuels running out, and that their continued use could be destabilizing the planet's natural ecosystems and the global climate. The development of nuclear energy following World War II raised hopes of cheap, plentiful and clean alternative to fossil fuels. But nuclear power development has stalled in recent years due to increasing concern about cost, safety, waste disposal and weapons proliferation. Continuing concerns about the sustainability of both fossil and nuclear fuels use has been a major catalyst of renewed interest in the renewable energy sources in recent decades. Ideally, a sustainable energy source is one that is not substantially depleted by continued use, does not entail significant pollutant emissions or other environmental problems, and does not involve the perpetuation of substantial health hazards or social injustice. In practice, only a few energy sources come close to this ideal. Renewables appear to generally be more sustainable than fossil or nuclear fuels. They are essentially inexhaustible, and their use usually entails much lower emissions of greenhouse gases and other pollutants, with fewer health hazards. So it seems likely that they will form an increasingly important part of our energy mix in the future.